Hello, my name is Hamza Balsharnik, and this is my final project, Conflict Situations Monitoring for Maritime Shipping. And this is the third time I'm trying to record this project. The first one, I couldn't record the screen. The second one, I couldn't record my sound. I hope this third time is a charm. So, we have a core question I set out to answer. Can satellite-detected thermal anomalies, when combined with conflict news, serve as an early warning signal for armed conflict in regions that matter to global shipping? I built a full data pipeline to answer this, and from satellite APL calls and web scraping all the way to machine learning classifiers and the publication quality dashboard. So let's start. I'm gonna move some different mixed. So at the first, we have setup parts. We import the needed libraries for the notebook to complete the work. We use Docker to database setup. And so the first part is data collection. I chose four regions. First region is Ukraine, because the Russia-Ukraine war disrupted Black Sea grain routes and European energy supply chains. The second one is Gaza-Israel, because of the active conflict since October 23 near Eastern Mediterranean shipping lanes. The third one is Yemen and Red Sea. We got Houthi rebel attacks on commercial ships through the Bab el Mandab Strait in 2024, causing global rerouting the Cape of around the Cape of the Good Hope, dramatically increasing the fuel and shipping cost, which also adds 10 to 14 extra days per voyage. And finally, we have Iraq, Syria on because of ongoing instability near major oil infrastructure, generate both real conflict signals and a lot of background thermal noise from gas flaring. Um, I'm sorry, I'm cold. That's why maybe I'm sounding bad, and I'm also really tired because of my sickness. So sorry for my mispronunciations and mistakes. I'm really tired. So for satellite data, I use NASA Firm's API, specifically the LIRS Suomi MPP standard processing dataset at 375-meter resolution. I looped through 5 days chunk across a 6-month window from January to July 2024, collecting bounding box queries for each region. In total, I have 151,000 raw records. Then I made some data cleaning, and at end I ended up with 1041 on 141,212 records, clean thermal detection records, and we can see each one here. The firm's data summary is can be seen here. Then I need to collect news from the internet. I used four source. The first one is Godot project, the second one is Google New RSS, the third one is multi-outlet RSS, the fourth one is, and final, Bing News RSS. These are all free and no API key needed. And because of this, it can take too much time to take the news data, and also, and it can change the number of the news titles taken from the source because of their free and limitations. So we have keywords like bombing, war, airstrike, shelling, missile, attacks, troops, etc., etc. And I have a relevance filter, which is article title must contain more than one conflict keyword or at least more than one region keyword. And I have a duplication uh, per region URL dedup during collection plus global URL dedup content. So after around 20 minutes collecting news. I get 1,368 global DDoP. One is duplicate, so it's removed. This number can change depend on the our free sources gives at what that time. But the main results almost stay same. And we have the summary of the news data, and we save the procedural database to like we can see here. Then we all data was stored in the PostgreSQL database running inside a Docker container, like here. Yeah, sorry. Then we continue with the spatial and temporal analysis. Raw forms data is just a cloud of individual satellite pixels. To turn these into meaningful events, I use DBS scan clustering with a Haversian distance metric, grouping detections that fall within 10 kilometers of each other into 3-day temporal bins. The result was 12,833 discrete thermal events, as we can see here. And almost 2% is noise singletons, and the other one's genuine multipoint clusters. We can see the number of events per region here, and mean FRP and mean durations here too. Each event has a center rate, duration, total fire radio power, and the day and night detection ratio also. So we got temporal patterns. The first one is monthly thermal event counting by region. As we can see here, Iraq and Syria and also Ukraine dominates this chart, like also this chart. This is the mean fire radiative power over time chart. Uh, Gaza and Israel and Yemen Red Sea lines are showing inconsistency, and Ukraine and Iraq shows higher numbers here. So then, sorry, we have day and night detection pattern by region table here. One of the clearing findings from the temporal analysis was Yemen's day and night ratio. 82% of the Yemen's thermal detection occurred at night. That is the highest night ratio of any region and is consistent with covert nocturnal military operations. For comparisons, agricultural burns in Iraq predominantly happen during daylight hours, but in Yemen Red Sea we can see nighttime, and this shows the correlation with the war or the attacks. The most of the detections are in Iraq, Yemen, and Gaza's nighttime, and only in the Ukraine we have a highly daytime detection ratio. Then we go to thermal events by region and top 10 high FRP hotspots per region charts maps here. Especially Iraq and Syria show the dense cluster of high FRP events along around this valley, and northern Syria consistent with gas flaring and industrial activity mixed with conflicts. Ukraine shows a brand split along the eastern front line. Gaza has a small geographic footprint but very high event density. And Yemen has this part of the map shows what on-land attacks happened or the detections happened. So correlation part, thermal and news correlation and classification. For the correlation analysis, I matched each thermal events to conflict news articles using three simultaneous criteria: same region, within 7 days of event start date, and at least one conflict keyword in the article title. As we can see here, and we got the results. The conflict association rates per region tell an interesting story is here. Ukraine has the highest percent, 40%, strong news coverage directly tracking to frontline activity. Gaza has 25.8 and Iraq and Syria has 24.2 percentages. And Yemen has the lowest association rate, 10%. But this association rate is low because of uh, this cause terminology mismatch. Yemen reporting mostly uses Houthi vessel seizure rather than standard conflict verbs like bombing, shelling. So that's why the news and the things doesn't match up. The terminology mismatch makes the Yemen association rate lower than the others. So when we compare each of them, we can see the number of article sources, events, articles per event, confliction rate, and average reporting lag days. So Ukraine has a almost 4-day lag after reporting. Uh, Average is almost four or around all the regions. Then we can see the news coverage by region. Articles are solid bars and the sources hatched bars, as we can see here. I think I'm sneezing. I don't know. I can't sneeze. Sorry. So this is an interesting chart. Conflict keyword frequency by region. And like I said, up Houthi has a 63.8% conflict keyword frequency. At Yemen and Red Sea, it's really high, the highest one, and we can see the most of it. The most common word we come across are war and attack. We also see a lot of drone. We see killed, and the least ones are like offensive, almost zero, and vessels. And these are the most common and least common keywords that we conflict. Then we go to statistical hypothesis test. Uh, the Mann-Whitney U-test comparing FRP distributions between conflict association and non-conflict event gives P equal 0.266. So we reject the null hypothesis. Conflict associated events do show a statistically significantly higher FRP distributions with a median of 15.1 versus 14.2 for non-conflict events, as we can see here. I don't have too much time, so I'm trying to get faster. There are other details we can see here and the result conclusions. So we continue with the machine learning class part. I trained 4 classifiers to predict whether a thermal event is conflict associated. So the machine learning classifiers are logistic regression, decision tree, naive Bayes, and SMV. We have the uh, yeah here confusion matrices and conflict associated classifiers. The decision tree has the best F1 score of 0.671, and importantly, it has a recall of 0.859. And this is uh, in risk monitoring context, recall matters most. We want to minimize false negative, uh, meaning missed recalls conflict more than you want to minimize false alarms. The most predictive feature was month, as we can see here. Decision tree feature importance. We can see the most predictive features for conflict association. Like I said, the most is month and capturing seasonal patterns in both conflict intensity and agricultural burn cycles, as we can see in this table. Then we go to dashboard, insight, and reflection part. So I have a 6 panel dashboard. The first one is thermal event conflict associated, where I, the colored part is conflict associated, non-conflict part. These are the parts we don't look, so it doesn't matter. As we can see, Ukraine also some parts of the Russia has really high conflict. Then we have Iraq, Syria part, which is also the biggest. Gaza and Israel shows a concentrated cluster in the southeast corner of the Mediterranean, and also Yemen shows a band along the Red Sea coast. Then we have the panel 2, which is conflict association rate by region. This is a bar chart and shows the Ukraine is like 40%, like we said, and Yemen is 10% as the lowest. The dashed line at the 50% gives a visual reference for a high risk threshold. And this panel directly answered the core question of the project, which regions have the strongest satellite news correlation. And we can see the Ukraine has the strongest. Then in the third panel, monthly thermal event frequencies, we can see it's dominated by the Iraq and Syria and Ukraine. They go up and down at some part of the month. We see consistent uh, lines at Gaza, Israel, and Yemen, Red Sea. In panel 4, we have machine learning classifier performance, F1 score, and recall are the our main bar here. The decision tree dominates both of them in four machine learning procedures. And then we have the panel 5, like I said before, in decision tree conflict classification, feature importance. The month is the most one, and then the others, which is has lower importance score. Final panel gives us FRP distribution by region. The total FRP, when it's low, we have higher density, but when total FRP increases, all of them goes almost to zero, really low densities. And then we come to written discussion and its three implication parts. The key finding parts are mostly talked in the uh, r- upper right. The Ukraine showed one of the strongest conflict association rates in the dataset, like we said. I think I can skip this right now. I spoke too much because so shipping and energy implications. Uh, Yemen and Red Sea is the biggest problem. Like we said, it costs too much and it uh, make latencies. So my recommendations uh, to management will be two things. First, pre-negotiate the Cape of Good Hope routing contracts whenever Yemen thermal FRP spikes. And second, use Ukraine thermal events frequency as a leading indicator for Brent crude futures hedging, since Black Sea route disruption correlate with European energy shocks. Third is the use the conflict association rate as a dynamic war risk insurance premium trigger. Any region above 35% as the fact sales computes from this run should automatically trigger enhanced coverage. And Iraq and Syria are special case. We have too much thermal detections, but the association is really low. So this is because a large fraction of those events came from securing crop residue burns and gas flaring at oil facilities. These are not armed conflicts. Applying a secondary filter of FRP above 50 megawatts combined with nighttime detection significantly reduces this false positive load. And limitations and future work. The main limitations are are in three parts. First is matching accuracy. Location dimensions are extracted from article titles only, not full article text. Second, firms can distinguish a conflict explosion from a wildfire from satellite data alone. The model compensates using FRP thresholds and the night detection ratios, but false positive remain. Third, sea-based attack, like I said, the Houthi threat produce no land thermal signature at all. Firms cover land surface only, which is a structural gap for Yemen. And these Also, we have the methodology here, and if I start over, I use the ACLAD Armed Conflict Events Database as a ground truth for training levels rather than news article matching as a proxy. I would also incorporate AIS vessel tracking anomaly data to capture sea-based Houthi attacks that land-based sensor miss. And I would extend the time series to at least 2 years to separate seasonal agricultural burn cycles from genuine conflict escalation signals. So, in conclusion, satellite thermal anomalies combined with conflict news provide a statistically significant and operationally useful signal for maritime risk monitoring. The data pipeline I built here demonstrates that this system can be maintained automatically, updated weekly, and scaled to any conflict-prone region in the world. That's all I want to say for my project. Sorry, the video is longer. But thank you for this semester. This lecture teach me more than I expect. It was fun and enlightening course. Thanks for everything and have a great summer.